Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Logarithmic Differentiation. Be sure you are an active learner while watching this video. Recall back in video lecture 23, we exploited properties of logarithms to simplify derivative calculations in problems already involving logarithms. In this lecture, we introduce logarithms into a problem to accomplish these similar simplifications. The process is called logarithmic differentiation, which not only simplifies the calculation of derivatives of certain functions, but also enables us to compute the derivatives of functions that we could not otherwise differentiate using the techniques developed thus far. Examples are always worth 1,000 words, so let's talk about this. Suppose we say differentiate y equals f of x equal x times x plus 1 times parentheses x squared plus 1. Now, this is a product, but it's a product of three functions, and it will be very involved differentiating this using the product rule, and then you would have a lot of complicated simplification using algebra to do this. You could do it other ways, but those would be the consequences of doing it this way. What we're going to do now is we're going to use what is called logarithmic differentiation. So first thing we're going to do is we're going to take the logarithm, and I'm going to use the natural logarithm for simplicity, of both sides of the equation. So we're going to say that the natural log of y, this side, is the same thing as the natural log of this product here. But now we're going to use the properties of logarithms to say that this is the logarithm of the product, so it's going to be the sum of the logs of the factors. So we will have ln of y is equal to ln of x plus ln of x plus 1 plus ln of x squared plus 1. And now we're going to take the derivative with respect to x of both sides of this equation. Now, recall when we're taking the derivative of the left-hand side, y is a function of x. In fact, y was exactly this function. So we have to use the chain rule. So first on this side, when we take the derivative, this is going to be 1 over y times dy dx. So you see that's what we're going to get on this side is 1 over y dy dx, and that's showing over here. I'll talk about it later, but this is 1 over y times dy dx. So you see we get dy dx over here, and we're going to solve for that in a bit. But then we take the derivative of this. This is the derivative of a sum, is the sum of the derivatives, but these derivatives now are quite simple to compute. This derivative of ln x is 1 over x. The derivative of ln of x plus 1 is 1 over x plus 1, and the derivative of ln of x squared plus 1 is 1 over u times du dx. That is the chain rule. So now if we talk about what we have on this side, then we have 1 over y times y prime. And on this side we have this. Now the problem was asking us to find y prime. So what we're going to do is multiply both sides of this equation by y. And so we'll have y prime is equal to y times all of this business. But y, we knew from the beginning of the problem, was this. And so we write what y is, and this is what y prime is. Most of the time I was talking, this can actually be done very quickly and is a very powerful form of differentiation. Now this was an example of using logarithmic differentiation. Let's define what it is. These are the steps. So finding dy dx by logarithmic differentiation, take the natural logarithm on both sides of the equation and use the properties of logarithms to write any quote-unquote complicated expression as a sum of simpler terms. Then we're going to differentiate both sides of the equation with respect to x, and realizing that that means we're going to have to use the chain rule at least on the left-hand side and maybe other places. And then what we do is we solve the resulting equation for dy dx. So this is your process. Let's do another example. Here, and this is much more complicated, we're saying differentiate y equals f of x is x squared times x minus 1 times x squared plus 4 whole cubed. Again, this is 3 terms in the product. You have a power here, you have chain rules. So it's actually reasonably complicated. To take the derivative and then doing the algebra would be complicated, and so on and so forth. Let's see how this works doing this using logarithmic differentiation. So we start with y equal this business, and then we'll take the natural logarithms of both sides. So the ln of y is the ln of all of this business. And then, since this is a product of functions, this is the same thing as the ln of x squared plus the ln of x minus 1 plus the ln of x squared plus 4 whole cubed. But then we have the property of logarithms that say the exponent up here can be brought in front of the expression. So the ln of x squared is 2 times the ln of x. This stays as it was, but here that 3 comes out in front, and that is 3 times the ln of x squared plus 4. So now what we're going to do is, this was all algebra or pre-algebra, but now we're going to do some calculus. We're going to take the derivative of both sides. The derivative over here is the derivative with respect to x of ln of y. We'll talk about what that is later. Well, I guess we'll talk about it now. That is 1 over y times dy dx, or y prime. That's the chain rule. And then I do each of these terms. Now the 2 just sits there and the 3 just sits there. So the derivative here is going to be 2 over x. The derivative here is going to be 1 over x minus 1. And the derivative here is going to be 3 times. And the derivative of this is 1 over u times du dx. So now what we're going to do is multiply both sides by y, like this. And now we've solved for dy dx. But now we're going to put what is y, and y is all this business, so I put all of this business here. So you see, rather quickly, we have found the derivative of y in a nice form that we can substitute numbers in. Here's an applied example. So the population of a town T months after opening is given by, and this is P of T is equal to, and it's 1800 e to the minus ln 9 e to the minus 0.3 t. What is the relative rate of growth of the population 6 months after opening the plant? Well, you see, that's complicated, and we got the t is way up in the exponent, so we're going to take the natural logarithm of both sides. So the natural logarithm of p is equal to the natural logarithm of what we had on the other side, but that's going to be the sum of, so it's the ln of 18,000 plus the ln of e to this business. But the ln of e to this business is just that business by properties of logarithms. So the ln of p of t is the ln of 18,000 minus ln 9 e to the minus 1 t. I'm sorry, I misread that before. Okay, so now we're going to take, we've just done pre-calculus so far, but now we're going to take the derivative of ln of p. So that is going to be 1 over p times p prime. And so that is what we have, and that's going to be equal to, the ln of 18,000 is a constant, that's going to be 0, and the derivative here, the constant comes through, but then the derivative of e to the u is e to the u. So p prime over p is equal to this when you simplify it, and we do have some minus and minus action going on here. Make sure you do look at this with pencil and paper so you understand what is going on. So therefore, we're trying to find this 6 months after the opening of this, so we're going to evaluate this at t equal 6. And again, we were asking for the relative rate of growth, so that really is p prime over p. So we plug in t equals 6 into this and into a calculator, and we get this. And so 6 months after the opening of the plant, the relative growth rate is approximately 12.1% per month. That's a very healthy growth rate. Let's look at 2 more examples before we finish this. Now here I'm starting with a function that is y is equal to x to the 5th over 1 minus 10x times the square root of x squared plus 2. The reason I'm doing this is involves products and quotients. So we start as we did before. We take the natural logarithms of both sides, and we write then the ln of y is equal to the ln of x to the fifth minus the ln of the product, because the product is in the denominator and the logarithm of a quotient is the difference of the logarithms. But then I'm going to say that this inside is a logarithm of the product, which is the sum of the logs. Now notice I'm distributing this minus sign across the sum of the logs, so that's why that's minus and that's why that is minus. Now, still doesn't look simple, but now we're going to use the properties of logarithms a little bit more. And we're going to take derivatives and so forth. So what we do is when we take the derivative of this ln y, again we get 1 over y times dy dx, or y prime. I take the derivative of this one, that is 1 over u times du dx. So I get x to the fifth over 5x to the fourth. When I simplify that, it's 5 over x. Then I take the derivative of this. There's my minus sign. But then when I take the derivative of this, it's going to be 1 over u times du dx. So I get a minus. It's going to be a plus. So that is 10 over 1 minus 10x. And then this last one, what I'm going to do is I'm going to take the derivative of this. So this is 1 over u times du dx. Well, the derivative of u with respect to x is 1/2, that business to the minus 1/2 all over 2x. And if you simplify that, you see that some things can be combined with exponents. That is x squared plus 2 to the minus 1/2. And so you move it into the denominator and you simplify it. The 2's cancel and you get this expression. Then we're going to multiply both sides by y, as we've been doing. Then we're going to put what y is in terms of x in that place. So you see we found y prime here. And so what looked like a horribly complicated problem using quotient rules, product rules, chain rules, so on and so forth, and then a lot of algebra on top of that, becomes quite manageable. Now, depending upon the person, this might be only slightly easier, but for many people it's a lot easier. And the answer is almost definitely simpler than what we've got using that, because the simplification kind of, you get it for free. Let's do one last example. You might recall at the beginning of this lecture, I said we could do problems that we couldn't do before. Here's an example of that. We're going to differentiate y equals x raised to the x power. Now this is a beast we have not run across because x is in the base and x is also in the exponent. And you would be flummoxed. You would not know how to approach this. But we've learned logarithmic differentiation. And so, you see, we got the x both places, so we can't use this law and we can't use this law. We have to do something else. So what we're going to do, though, is we're going to take the natural logarithm of both sides. So the ln of y is the ln of x to the x. But then I'm using the property of the exponent here. This is x to the x, so that's the same thing as x ln x. So you see, this is now a product of differentiable functions of x. This is x times the natural logarithm of x. So now what we're going to do is differentiate implicitly on the left-hand side. So that's going to be, again, 1 over y times dy dx, or y prime over y. And then this is going to be the product rule. So it's the derivative of the first, which is 1, times the second, ln x, plus the first x times the derivative of the second, which is 1 over x. And this is ln x plus 1. Again, as we always do, we multiply by y. So y prime is equal to this. And then we replace y prime with what it was. And we get this as an answer. Very powerful stuff, this logarithmic differentiation. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.